Okay, so we're going to quickly look at our next sort of major important derivative rule, which is the product rule. So what the product rule is, it's used whenever you have a function multiplied by another function. So we see that going on here. We have x squared minus 1 multiplied by 2x cubed plus 2x. So one might think that in order to do the derivative of that, what you hope would be true is you do 2x, like the derivative of the first thing, times the derivative of the second thing. And you should quickly see that that is completely wrong. Like there's no way that's right, because this thing overall is a fifth degree. If you were to expand it out, you get x cubed times x squared, so that would be degree 5. So its derivative should be degree 4, but we see that this is in fact just degree 3. So we know that that is in fact wrong. We can't get the derivative that way, which is kind of unfortunate, but there is a nice handy dandy formula. So you kind of call the first function f and the second function g. And the formula works out to this: derivative of the first times the second plus derivative of the second times the first. So this is sort of a short form way of writing. I should be writing f prime of x and g of x, so on and so forth. It's also kind of a terrible abusive notation because overall this function is f, and I called this piece also f, so technically I should use a different letter for that. But the way the formula is written is normally with f's and g's, so if we're comfortable using just f's and g's and we understand in the formula it means part, and the overall function can be called whatever it wants. I'm okay with that if you're okay with that. If you want to change this function to an h so that you have all different letters, I'm fine with that too. So however you want to handle it is how you handle it. But how it works out, I know I go off to the side just for organization. And write out the different pieces just kind of off to the side. F prime, F and F prime, G and G prime just helps keep things organized as they get more and more complicated. And then I'll put the pieces together in the way that they go. 2x times G, 2x cubed plus 2x plus G prime, there's the 6x squared plus 2 times F, x squared minus 1. So that is in fact the derivative of that function. You have absolutely no reason to believe this works right now, so if you wanted to pause, you could do this kind of the long way, expand this out so that it's just a single polynomial, get the derivative of it, and then expand this out, and you should see that the two things are in fact exactly the same. So that's something you can do. I'm going to actually prove that this product rule works below, so I'm not going to go through all the expanding. I'll keep this video a bit shorter. So that's how this rule works. You do the f prime g plus g primed f. I want you to, even though it would be the same if you did g primed f first and f prime g second, I want you to memorize it in this order, because the rule that I show you in the next video is going to have a subtraction instead of a plus when we do quotient rule, so the order will matter there. So let's just make the order matter now. So start with the first thing's derivative first. So f is first, f primed first, and then mix and match f prime with g, g primed with f with a plus sign. Memorize it in that order so that well, you're going to want to memorize it because you're going to use it a lot in this course, so it's not a tough one to remember. It's easier than looking it up every time. Memorize it in that order. So formally stated, if you have h of x, which is f of x times g of x, where f and g are both differentiable functions, then we have h primed of x is f primed of x times g plus g primed of x times f. Wonderful. So I'm going to go through the formal proof again. Not something you'll ever have to reproduce, but it's nice to see this proof. I think it's a wonderful proof. It's one of my favorites in all of math. It's kind of beautiful. So You have to go from first principles because, again, we don't have this rule yet. So anytime we need to build a new rule, we kind of have to start with first principles. So there's h of x plus h. So h is f times g. There's it with x plus h's filled in. And you see right away, like, it looks like there's nowhere to go. It looks like there's nothing that can actually be done. And so what I do here is I do my favorite mathematical trick, which is to add 0 creatively. And here's the argument of why this maybe works. So there's my two terms there. What I'm going to do, I'll switch colors so you see the thing that I'm adding in, is I'm going to put this here. And I'm going to put this here because then I can kind of factor out a g of x plus h from those two terms, and I'll be left with something that looks like the derivative of f, because I'll have f of x plus h minus f at x with the h on the bottom. That's my hope, is maybe if I put that in there, it'll just so happen that I can have an f primed, and then maybe I'm at least getting somewhere. And obviously you can't drop that term in there without sort of adjusting, because I've just changed the overall equation. So to keep everything the same, I'm going to make it so that I am adding 0, so that I haven't changed the function. So if I'm subtracting that, I'm going to add it as well, so that it's the exact same function as the line before. Maybe give myself some more room somehow. And then there's my idea was the limit as h goes to 0. My idea was kind of factor out that g of x plus h from the first two terms. So the first two terms then are that. So I'm just dealing with these terms that you can kind of see on screen there, just these first two terms. So I'm factoring out this g of x plus h completely out front, and then I'll write the rest as a fraction, f of x plus h minus f at x over h. And then I'll look at the other two terms, and f of x is common to those terms, so maybe I'll do the exact same thing. Again, that over h is on the line above. Maybe I'll do the exact same things with that, and I'll factor out that f of x and see what I'm left with. So I'm left with g of x plus h minus g of x all over h. And by golly, that piece, that fraction, after I factor out this common f of x, that fraction, that looks like the derivative of g of x. And that's kind of interesting. And that's why I love this this proof, because my idea is, okay, I'll just stick this term in here because maybe I'll be able to factor and get the derivative of f. And the wonderful thing about this proof is that's my idea. If I have to put that there, then I have to put the plus f of x times g of x plus h, but that just so happens to be exactly the thing you'd need to do the same trick with the g's. So it kind of works out perfectly. It's kind of beautiful in that way. And then the idea here is I've got this separated into sort of 4 different parts. And our limit rules say I can break it into 4 different limits as long as I know that those limits exist. So as h goes to 0 of this n piece, again, that's just the derivative of g. So that's going to exist. That's because we said g was a differentiable function above. So the limit as h goes to 0 of just this n bracket is the derivative of g. The limit as h goes to 0 of f of x, well, that's just f of x. There's no h in there, so it doesn't matter what h does. So that limit's going to exist and work. This one here is the derivative of f as h goes to 0. So that's going to work because we said f has a derivative. And the last one, it looks like it's an obvious limit. It's the limit as h goes to 0 of g of x plus h. And what we really want to happen is for that to be g of x. And it looks obvious, like as h goes to 0, shouldn't it just go to 0 and you're just left with x? But it might be something like this, where if you take one small step off of g of x, you jump to a completely different area. So it's not necessarily true in general that if you take a little step off of x that you're still close to where you were before. But what's wonderful here is we've decided g is a differentiable function, so it has a derivative. So if this g of x plus h minus g of x over h, if that's going to exist, that has to be a 0 over 0 limit. The function can't look like this if the derivative is going to exist. The function has to be sort of nice and smooth. So if you take one small step off of any point, you're not going too far. So that would, in fact, converge to that limit as well. And there we have it. There's my QED. That's the signaling that I have finished my proof in an old school way. If you didn't have me when I taught, if I didn't teach you trig identities, you've probably never seen that before, but it's some old Latin that just says my proof is over. Okay, so there's the wonderful proof that this formula does in fact work. So what we're going to do now, you've seen me use it once, you're going to do it a bunch of times. So again, see if you can write the f and g like so. Write them off to the side. X minus 4, the derivative of f is blah, g is 2x cubed minus 5, g primed is 6x. So I'm filling it in for you. Derivative of that is 1. Get your different pieces off to the side and then see if you can fill into the formula. F prime g plus g prime f. And again, you can shorten and not write all the of x's if you don't want to, just when you're writing out the formula. I'm okay with that. So pause the video for a second, see if you can work through these examples, and then unpause and you'll see me work through all these examples. So again, I already did the pieces of this one. So I'll just write out those different pieces. F prime g, g prime f, like so. And again, we're just doing first line only. You would, if you had to do anything with that, you'd probably want to expand and simplify and all that wonderful stuff. There's the different pieces, putting them together. F prime g plus, I can't even fit it all in on my screen, g prime 6x minus 4 f whole cubed. So there's that one for me. Okay, this one, your f is just the x cubed. Your g is that whole expression, 2x squared minus 4x to the power of 4. F prime, nice and easy, 3x squared. G prime, we got to remember our skill 1, that's a chain rule, so the 4 comes down, becomes a 3, the inside stays the same, and then the chain rule says multiply by the derivative of the inside after the fact. So there we go. Putting all those pieces together, f primed g plus g primed, ooh, big mess, 4 times f x cubed. And again, if you had to do anything with that, you'd probably do some, I would look for some common factors first, because you have power of 4 and power of 3, so common factor stuff out first, and then expand the rest and clean it up. I was going to switch colors back and forth so my examples don't bleed together, and I forgot to do that. Okay, next one. Your f is the x squared minus 2x. anything f prime 2x minus 2. Your g is the cos of 4x minus 3. Again, remembering the other video, derivative of cos is minus sine. Leave the inside in there, then multiply by the 4 after the fact. F prime g, so 2x minus 2. I guess I'm writing equals every time. Terrible communication. So this is the derivative of the function above every single time. Terrible communication, Mr. Clement. So the derivative of this function, f primed times g plus g primed. When you write g primed, you might want to swing the 4, so it's a plus. You might want to swing that 4 in front, so I'm using the plus and the negative to just make it negative. And then swinging that 4 to the front of the term, that's where it normally goes anyway. G primed and then f x squared minus 2x at the end. The last one. Switch colors back and forth. I forgot. Derivative of sine is cos. Leave the inside function there. Then separately multiply by the derivative of the inside. That other function is this. It's cos squared. So remember, you got to think of that as the whole thing to the power of 2. And we're going to get some super chain rule stuff happening there. So 2, the 2 drops down, becomes a 1. And then we're going to multiply by the derivative of the inside. The inside function is a cos, so its derivative is going to be a sine. And then once more, derivative of the inside of that is just 4. So there we go. So the derivative here, maybe I'll use Leibniz notation. dy by dx is f prime g. Okay, so x squared minus 4x plus 4 times 2x minus 4 f prime times g, which is cos squared of 4x minus 2. Plus g primed, and if you want to start to clean that up, you don't have to. You could just write all of this out as it is. There's a minus, a 4, and a 2, so you can actually make that minus 8 cos of 4x minus 2 times sine of 4x minus 2. G prime times f, so there's another sine of the big ugly quadratic minus 4x plus 4. And I think I got it. So there's that example there. Leave it on screen in case you want a second to pause and look at it. And then this last example, find all values of x where the tangent is horizontal. So f is a product rule. So we're going to have x minus 2 to the power of 3. Chain rule says the 3 comes down, becomes a 2, the inside stays the same, and then you multiply by the derivative of the inside, which is just 1. Same sort of thing. The 2 drops down, becomes a 1, multiply by the derivative of the inside, which is just 1. So f prime of x is going to be f prime g plus g prime x, so f prime. I'm not going to write the times 1. F prime g plus g prime f. So there we go. And what we're trying to do here is we're trying to find horizontal tangents. So we're going to find where this thing is equal to 0. In order to do that, we need to have this whole thing factored. Now, it would be an absolute nightmare if you were to start expanding everything and then try and factor the big long thing at the end, because the big long thing at the end is going to be 2, 4, 4th degree, it looks like. That would be not so fun to factor. So whenever you do this, just the way this rule works, you're always going to have lots of common factors. So I see x minus 2 squared and x minus 2 cubed in the two terms. So I can factor out the x minus 2 squared. there's an x minus 1 to the 1, an x minus 1 to the 2, so I can factor out at least one x minus 1, and then I can rebuild the rest. So what am I left with? I'm left with the 3. I've got both of these out front. I've got one of those out front, so I've got that. Plus, I'm left with the 2. This is out front. I've got 2 of those out front, so I'm left with just 1 on the inside. And then from there, all I have to do is clean up the inside bracket. So I got 3x and 2x, so that's going to turn into a 5x. I've got a minus 3 and a minus 4, so I think that's minus 7 overall. So if I haven't messed that up, I can now read off my answers. I get x equals 2, x equals 1, or x equals 7 over 5 as the values where that derivative is 0. So those are the values where the tangent is horizontal. I can put that in a nice concluding sentence if I wanted. So those are my examples. So you can summarize in your own words how this rule works, what the formula is, all of that. Take a stab at these exit card questions. We'll take them up when you get to class. And then you can work on this practice in class.